Welcome viewers to the sixth lecture for the online series of lectures for the course of differential geometry. Um, we are going to start this lecture with, with the discussions on tangent space. The tangent space. So now for the tangent space, we need to define a germ of C infinity function set at a point P on a given manifold. So we are going to define a germ of a smooth function at P in M. So we have a fixed point P in M, and we are going to call a germ of C infinity functions at P in M to be an equivalence class of smooth functions defined in some neighborhood of the given point P on the manifold. Okay, so now we need to define what this equivalence relation is, based on which we will have these equivalence classes of smooth functions on defined in the neighborhood of the point P in M. So two functions of this sort, meaning that two functions in the same class will satisfy the following property. In other words, two functions of this sort are called equivalent if they agree on some possibly smaller neighborhood of P, meaning that the the open set on which they agree with each other may be a smaller set than the open set that we started with. Okay, so the set of all germs of smooth real valued functions at P in M is denoted by Cp infinity of M. So the elements here in this set are equivalence classes, something like this. Okay, so two functions belonging to this equivalence class are going to be equivalent to each other. Okay, so suppose f, so we put a subscript here to emphasize that they are germs of smooth functions at P in M. Okay, so this is an equivalence class. So if we add two equivalence classes, meaning that we are adding two elements here, um, the definition of addition in so it, in this set is given by this. Okay, so we number this by 1. Okay, where this f plus g here is defined pointwise. That is f plus g at x is equal to f of x plus g of x. Okay. And we can also define a product of two elements here in the following way. The product of this is given by uh, this straightforward way, okay, where this product is again defined pointwise. F dot g at x, okay, is equal to f of x times g of x. Here f and g are both smooth functions, real valued smooth functions. They are functions from M to R. Okay. I want you to check the well-definedness of this definition of addition. Let me do that for you. Let me check that this is indeed well defined. Let um, f is equivalent to f prime. What does that mean? It means that uh, they belong to the same equivalence class, right? In other words, they belong to the same germ of smooth functions defined at the point P in M. Okay, so then according to the definition of the equivalence relation, there exists um, U, there exists a neighborhood of P, right? A neighborhood of P. In other words, U is an open set containing P such that f restricted to this open set is equal to f prime restricted to this open set. That is, f and f prime agree with each other on this open set U. containing P, right? So that was the definition of this equivalence relation. Now also let G being equivalent to G prime, so that there exists V be, there exists an open set V contained in M, so that P is also contained in this open set, such that um, G restricted to V is the same as G prime restricted to V. Okay. Now it's immediate that on this intersection, um, well, no, on this intersection, let us first define f plus g. Okay, so we are going to define this function, right, where x belongs to this open set u intersected with v, and f plus g evaluated at x is defined as f of x plus g of x. And based on these two equalities, we immediately see that f of x is equal to f prime of x and g of x is equal to g prime of x. Why is it so? Because on u intersected with v, f of x is equal to f prime of x and g of x is equal to g prime of x, right? Because f of x is equal to f prime of x on the open set u, and g of x is equal to g prime of x on the open set v, so they should also be equal on the intersection. Okay, so right, this, according to this definition, it is nothing but the sum of these two functions, right? So we have found an open set on which these two functions agree with each other, so that f plus g is indeed equivalent to f prime plus g prime. So this verifies the well-definedness of uh, the definition 1 of addition of two elements in the set of germs of smooth functions at point P on the manifold M. Okay, so similarly you can show that equation 2 is also well defined. The product of two elements in the set of germs of smooth functions at the point P on M, right? If I pick up two elements from here, then I can, so according to 2, I can define the product of two elements here as the product this way, and we can verify in similar to this equivalence relation that this is also a well-defined product between two elements here. So with respect to 1 and 2, so 1 tells us how to take addition of two elements here, and 2 tells us how to take product of two elements here. So with respect to these two definitions, the germ of smooth function set P in M becomes a ring. Okay. Now let us define uh, or let us put the vector space structure on this set. Okay. So we have seen that it becomes a ring a while ago with respect to a well-defined addition and product between elements here. Okay, now we already have addition of elements, right, according to equation number 1. Now we are going to define scalar multiplication in this set, and the scalars will be coming from the set of real numbers. Alpha is any real number, and this f sub p is an element, is an equivalence class or a germ of smooth functions at P in M. Now we define the product of alpha with this element to give a new element here that is going to be alpha FP. Sorry, alpha F sub P. Okay, so this is the definition. So where f is of course a smooth function, a smooth real valued function on M, right? And how is this guy defined? This is defined in the following way: alpha times f is a function, is a real valued function on M, defined in the following way. This is alpha times f of x. Okay, so the right side is a real number, so this is how we define this function, alpha f. Okay, now uh, let these two equivalence classes are the same. In other words, we want f to be equivalent to f prime, that is f is equivalent to f prime, so that from the definition of this equivalence relation we know that there exists an open set in the manifold M with P belonging to this open set, so that U is an open neighborhood of P, such that f restricted to U is the same as f prime restricted to U. That is, f of x is equal to f prime of x for all x in this open set. Okay. Now this implies that alpha f of x is just multiplying both sides with this real number alpha. This is equal to alpha times f prime of x for all alpha belonging to the set of real number, right? Which means that we have been able to find an open set on which these two functions agree with each other, right? Alpha f restricted to U agrees with alpha f prime restricted to U, right? Which means that indeed they belong to the same equivalence class. Alpha f sub p is equal to alpha f prime sub p. Good. Which means that, so let me number this with 3. So it means that this equation 3 is also well defined. Hence, 3 is well defined. Okay, so with respect to 1, which is the vector addition of two elements here, and with respect to the scalar multiplication, Cp infinity m becomes a real vector space. is a real vector space. Okay, but it in fact we can tell more. We can put more structure to this real vector space to make it in make it a real algebra, or it's an R algebra, because it also has multiplication of vectors, right? You can multiply two elements here, okay, and you can check that this product is associative, and it satisfies, this product satisfies, the product and the addition satisfy all the required distributive properties to form a real algebra, okay, an R algebra. So so this is how we find various algebraic structures in this set of equivalence classes of uh, smooth functions defined at P in M. Okay. Now we come to the very important definition of point derivation that will be required to identify the tangent space to a manifold. So the next definition is that of a point derivation. Point derivation. A point derivation of Cp infinity m. Okay, Cp infinity m is is a ring. Cp infinity m is an R algebra. Okay, so a point derivation of Cp infinity m is a linear map d sub p which takes Cp infinity m to the set of real numbers, okay, such that the following properties hold. The following property holds: dp acting on um, two functions here is going to be equal to dpf times g of p plus f of p times dp of g. All right, so dp of f times g is supposed to be a real number, right here. And on the right side, we also have a real number, because dp of f is a real number. We multiply that real number with g of p, because g is a, so all these functions, these two functions, f and g, are functions from m to r, right? So uh, so this is a real number, this is a real number. The addition of two real numbers is again a real number. So on the left side, I have a real number, and on the right side, I have a real number. I want these two real numbers to be the same. That's the property. So if this property is satisfied, we say that this map, this linear map dp, is a point derivation. Okay. So now the definition of a tangent vector. Tangent vector. A tangent vector x sub p. We always place a subscript when we are denoting a tangent vector, okay, in order to emphasize uh, that we are considering a tangent space to a given point on the manifold, okay, and this tangent vector belongs to that tangent space. We'll come to the notion of tangent space in a while. Okay. So a tangent vector x sub p at the point P in M is a point derivation at the point P. The so if I pick up all the tangent vectors at the point P, I end up forming a vector space which we denote by T sub P M. Okay, so the tangent vectors at P in M form a vector space denoted by TPM. Okay. Okay. So now we learned towards the end of lecture 4 that given the standard coordinates r1, r2, all the way up to rn on r to the n. Okay. So how are these functions defined? So if r1 acts on an element v, right, an n-tuple from this n-dimensional Euclidean space. Okay, so how do you write v? It's an n-tuple, v1, v2, all the way up to vn. Okay, so if you choose the function ri and you acted on this element of the Euclidean space R to the n, you just pick up the real number vi, the ith component of that vector. Okay, this is how you define this function Ri. So each Ri is a function from R to the n to R. Okay, it's a real valued smooth function on the Euclidean space R to the n. And given a neighborhood u comma phi, which we denote by u comma x1, x2, all the way up to xn, about a point P in M with, so how do we get these local coordinate functions out of this standard Euclidean coordinate functions and this homeomorphism phi? Remember? So remember that xi was defined to be equal to ri composed with phi, okay, which is a map from u to r, right? So for it acts on an element here in this open set, right, first. And under this action, it is taken to a vector in the Euclidean space R to the n. Then when that vector is acted upon by Ry, we end up with a real number here. Okay. Okay. Now one defines partial derivatives. We have learned it towards the end of lecture 4. I'm just reviewing that. So how did we define this partial derivative with respect to the ith coordinate function, local coordinate at P in M? So this is how we defined it, right? This was defined as with the help of this standard coordinates in the Euclidean space, this partial derivative of f with respect to the coordinate xi is defined as follows. Okay, and we know that this is a real number. whatever we have here is a real number because we are evaluating at the point phi of p, with f being a germ, an element, f is a function in one of the germs. Okay, so we number this by 5. This is how we define partial derivatives. We have seen it earlier. Now, one needs to verify that these partial derivatives defined by equation number 5 satisfies the point derivation property given by equation number 4. So let us see how we verify it. F times g, okay, is, so we need to verify this. This is not equal. We are going to prove, or we are going to verify that this holds. Del xi at p acting on f times g of p plus f of p del xi at p acting on g. This is equation number 6. Okay, and this holds for all f and g in this R algebra. Okay. So it needs to be verified. So if we start with the left hand side, then we immediately see that from the definition of these partials, these it can be written down as, from this definition, equation number 5. This is del ri at phi of p acting on f times g composed with phi inverse, right? So this is going to be equal to del by del ri at phi of p, acting on f composed with phi inverse times g composed with phi inverse. Okay, so how do we see this? So here is a side note. So what is f? F is a germ. F belongs. F is, so it's an abuse of notation though. By f, simply f, I mean an element here. Although it's an equivalence class, I just mean that f is a function from one of those equivalence classes. Okay, so is g. Okay, and how do you define f times g? It's defined pointwise, as we have seen earlier, f of x times g of x. Okay, and where are these guys living? F composed with phi inverse and g composed with phi inverse. These are also functions, and they belong to c phi of p, c infinity sub phi of p of m, right? Because they are going to be evaluated at the point phi. So, there exists neighborhood of phi of p on which these functions are defined. Okay, so so you take this function, and I take this function g composed with phi inverse. Okay, and is going to be uh, evaluated at phi of x, right? And according to the straightforward definition of the product of two functions uh, in the germs of smooth functions, is going to be equal to f composed with phi inverse evaluated at phi of x times g composed with phi inverse evaluated at phi of x, right? So immediately we see that this is equal to f of x times g of x, right? On the other hand, if we take f times g composed with phi inverse and trying to evaluate it at the point phi of x, we see that this is equal to f times g evaluated at x, right? And by the pointwise product, by the definition of the product of uh, two germs, we know that this is equal to f of x times g of x. Hence, this is equal to this. Hence, we have this equality. Okay, all right. So let me erase this part now. I don't need it anymore. So this is equal to now now I'm going to equal to, this is equal to um, um, so well, this is the standard uh, rule of derivative, right? Because we are now doing everything in r to the n, so the Leibniz property holds, right? So this is del r I sub phi of p will act on this guy first, f composed with phi inverse and g composed with phi inverse evaluated at phi of p, right, plus f composed with phi inverse evaluated at phi of p times del by del Ri at phi of p. Now this will hit this latter function g composed with phi inverse. Okay, so now going back to the definition of partials here from equation number 5, we see that this is equal to del by del xi at p acting on f, and this is nothing but g of p, right? And this is f of p times, and this is nothing but del by del xi at p acting on g, which is what we needed to verify, right? This one. Okay, so we verified that these partials are actually point derivations. Okay, now we are going to define the differential of a map, of a smooth map between two manifolds. We learned about smooth maps between manifolds earlier in lecture 4. Now let f from n to m be a smooth map between two manifolds, between manifolds n and m. So at p in the manifold big N, big F induces a linear map between tangent spaces TPN and T sub FP of M. So denoted by F star comma P, which is a map from TPN to T sub FPM. And this is defined as follows. If X sub P is in TPN, we have mentioned it earlier that the elements of the tangent spaces are tangent vectors. We are yet to prove that that actually forms a vector space. We will find it soon that it is indeed a vector space. The tangent space is a vector space, and we'll find the basis of this vector space. Now, if I have a tangent vector x sub p from TPN, then f star comma p acting on xp is supposed to be a tangent vector here, right? So this is a tangent vector here, and it is going to act on a germ of smooth functions, where in C sub fp infinity m, right? Remember, f goes from where to where? From n to m. And small f is here, right? So it is a germ of smooth functions at fp in m. So what is f composed with big F? So f takes n to m, and then f takes, a neighborhood to, of f of p to r, right? So it's supposed to be a function from n to r, right? if appropriate restrictions are taken. So we're not going into that, that will make the notations more cumbersome. So so that yeah, it is supposed to be a map here, F composed with big F. Yeah, because we are choosing P to be in N, right? So that F composed with big F is our germ here, Cp infinity M. So now we are going to define it like this, right? xp. xp is a tangent vector here, so it's going to act on a function here. Sorry, why am I writing it m? It should be n. It should be n. So it needs to be corrected in the note as well. It should be n. So good, xp is acting on this function here, right? Which makes sense. So this is, so, and this according to the definition of tangent vector, the tangent vector acts on on a germ of smooth functions and spits out a real number. Okay, so this is the definition of, so this is the definition of this linear map between respective tangent spaces. So here F is a germ at big F of P in M represented as a smooth function in a neighborhood at f of P in N. Sorry, f of P in M. Okay. So now we take the example of differential of a map between two Euclidean spaces. The special case of of a of a smooth map between two Euclidean spaces, and we'll try to find the differential of that map. Okay, suppose f from R to the n to R to the m is smooth at P in R to the n. Okay, suppose that it's a smooth map. So I want you to recall from the second lecture where we discussed various aspects of multivariable calculus required in the study of differential geometry, that such a function f is given by the following real valued functions, which are called its components. There are m components of this function big F. F1 is a real valued function of x1, x2 all the way up to xn, okay, where a generic coordinate of R to the n is given by these n coordinate functions. F2 of x1, x2 all the way up to xn, all the way up to fm x1, x2 all the way up to xn. Okay, we want, so when we say that it's a smooth map between these two Euclidean spaces, we want um, each fi being a function from Rn to R, these are all real valued functions on R to the n. We want each fi I from 1 to all the way up to m to be C infinity. That is the partial derivatives of fi with respect to this n coordinate functions in R to the n, x1, x2, all the way up to xn of all orders exist, and they're all continuous. Okay. Example, del kfi, right, and del xi1, del xi2, all the way up to del xik, okay, with I1, I2, all the way up to Ik are integers belonging to this finite set 1 to all the way up to n, the first n positive integers. Okay, so they can be anything. They can be k positive integers from this set of n positive integers. Okay, suppose we can have x1, then we can have x3, whatever we want. Okay, so all of them belong to this set. Okay, so these guys exist and they are all continuous. They exist for all such k in R. Okay, not, they have to be integers, of course, and are continuous at a given point P in R to the n. Okay, then we say that this function is a smooth map between two Euclidean spaces. We know it, but I wanted to review it. Let x1, x2, all the way up to xn be the coordinates of big R to the n, and y1, y2, all the way up to ym be the coordinates, standard coordinates on R to the m. Then the tangent vectors del x1 at P, del x2 at P, all the way up to del xn at P. Okay, these vectors form a basis for the tangent space T sub P R to the n, and the tangent vectors del by del y1 at f of P, del by del y2 at f of P, all the way up to del by del y m at f of p form a basis for the tangent space T sub f of p r to the m. Okay, we know it from our discussion from lecture 2. Okay, now the linear map f star comma p, the differential of f from tp r to the n to t sub f of p to r to the, sorry, this is small n, this is r to the m. Okay, remember the original function f was a map from r to the n to r to the m. Okay. So this map is represented, this linear map is represented by a matrix A J I at P. Okay, so these are numbers. Okay, the entries of this matrix AI A superscript I subscript J at P. Okay, these are basically functions, but when we are evaluating those functions at the given point P. So this relative to these two bases, so it's this linear map is represented by a matrix relative to these two bases as follows: f star comma p acting on del by del x j at p. Okay, this is a tangent vector here at tpr to the n, and this is equal to, since it follows from the definition of matrix representation of a linear transformation. We learned it in linear algebra, right? And since this is the matrix representation relative to these two bases, we must have this equality a j k at p. So just plugging in the entries from here, del by del yk at f of p, where k runs from 1 to m. This is equation number 8. So standard linear algebra, the where we study matrix representation of linear transformations. Now let me erase this front matter. Let fi is equal to, we are denoting by f superscript I to be yi composed with f, which is a linear map from r to the n to r. Okay, and we know that so these are component functions. F1 is a function of x1 x2 all the way up to xn. F2 is another function on x1 x2 all the way up to xn, and so on, etc. So let us write this equation number 8 as, rewrite equation 8 as follows: f star comma p acting on del xi at p to be equal to no, no, we're not rewriting it. I'm just writing it again here, because I'm going to start from here. K from 1 to m, a j k of p del del y k at f of p. So now it's a very standard technique. It's going to be used many times later. Um, we are going to hit both sides on the coordinate function yi. Okay, evaluate both sides on yi to compute the coefficients of this linear combination in equation number 8. So the right hand side is going to be equal to sum of all these expressions a j k of p del by del y k evaluated at f of p acting on yi, where k runs from 1 to m, and this is going to be equal to sum of all these expressions a j k of p del I k, Kronecker delta. Okay? And we know that if we compute this sum, then only the term that is going to survive is going to be uh, aj aj of p, aj of p. And what is going to be there on the left hand side? The left hand side is going to be equal to f star comma p del by del x I sub p acting on the function y I, right? And this according to the definition, of the differential is del by del x I, sorry, I think it was xj, right? Um, this was because j is here. I have to have j here, right? This is going to be j. So this is going to be j. So this is del by del x j at p acting on yi composed with f, right? Now this is nothing but del by del fi using the definition of these component functions. This is del fi by del xj at p. Okay. Therefore, we conclude that the matrix representation of this linear transformation f star comma p relative. So when we have a matrix representation that is indeed given relative to two bases, right, of the underlying two vector spaces, f star p relative to the bases del by del x j at p and del by del y at p, sorry, del by del y at f of p, okay, is this matrix del fi by del xj at p. Okay? This is precisely the Jacobian matrix of the derivative. Jacobian matrix of the derivative df sub p of f from Rn to Rm as discussed in lecture 2. Okay, so the differential, we have seen that, we thus see that the differential of a smooth map between two Euclidean spaces is nothing but its Jacobian matrix with relative to the standard basis of these two Euclidean spaces. Okay, the matrix representation of the differential, of course. So we have this smooth map between two Euclidean spaces, and there is a differential of this smooth map, which is a linear transformation, and we can represent this linear transformation with respect to the canonical basis of the two Euclidean spaces by the Jacobian matrix of the linear map between the two Euclidean spaces, of this smooth map between the two Euclidean spaces that we started with. Okay, so now it's time to discuss chain rule a bit. So we have discussed chain rule in detail for functions between Euclidean spaces in lecture 2, but now it's time to discuss chain rule in the context of manifolds. So here is the chain rule. I'm going to state the chain rule and then by means of a theorem, and then I'm going to prove it. Okay, so let f from n to m and g from m to p be smooth maps Okay, so in the previous, so what was the previous result about? We started with a smooth map between two Euclidean spaces, and then we have shown that the differential of this smooth map at a given point in the domain Euclidean space can be represented by its Jacobian matrix. The differential of this smooth map at a given point in the domain Euclidean space can be represented by its Jacobian matrix relative to the two bases of the given two Euclidean spaces, the canonical basis of the two Euclidean spaces. Okay, so that's what we have found. Now we studied the chain rule, right? So these are two smooth maps of manifolds. P is a point in the domain manifold, F star comma P, and G star comma F of P are linear maps between respective tangent spaces, between respective tangent spaces. So T sub Pn is mapped to T f of P m to T g of f of P P. So this first linear transformation is f star comma P, and this is G star comma f of p. So now theorem 1, the first theorem of this sixth lecture, states that if f from n to m and g from m to p are smooth maps of manifolds, smooth maps of manifolds, and p is in n, then the composition, remember the original map, so f is a map from n to m, and then G is the map from M to P, so that this map is G composed with F. So then the differential of this composed map, P is a point here, is equal to, so this map, this according to this theorem is G composed with F star comma P. So this is G star comma f of p composed with f star comma p. So this is a commutative diagram. Theorem 1 tells that this is a commutative diagram. Okay, this is equation number 9. So let us prove it quickly. Um, Proof. Let x sub p is in TPN, and let f be a germ of smooth functions at g of f of p in the manifold P. Okay, then one finds that G composed with F star comma P acting on XP, right? Because XP is an element here in this tangent space, and that is going to be evaluated at where. So this guy, the under the action of G composed with F star comma P, XP is going here, right? Is coming here. So it is going to act on a germ here. And this is equal to, from the definition of differential, we know that this is going to be equal to xp acting on F composed with G composed with big F. Okay, this follows from the definition of differential. This is equation number 10, and then we have um, G composed with, sorry, G star comma f of p composed with f star comma p, this thing acting on xp, right? Because the composition is, so if I take the composition, that is the, what is the domain of this composition? TPN. So it acts on xp, and the resulting thing is going to be here, right? So it the whole thing acts on a germ here. So according to the definition, this is a um, uh, what is this? This is going to be a real number, right? So this is G star comma f of p, and then from the usual definition of composition, it's going to be f star comma p acting on x sub p, right? And the whole thing acts on f. Now we apply the definition of a differential, and that tells us that this is just f star p acting on xp acting on f composed with g, right? Then again we apply the definition of differential to have xp acting on f composed with g composed with f. Okay, this is equation number 11, and from 10 and 11 it follows that from 10 and 11 it follows that G composed with F star comma P, since xp was an arbitrary tangent vector from this tangent space, this is equal to G star comma F of P composed with F star comma P. Okay, so this is the chain rule, and so this is how we prove the chain rule, QED. Good. I think it's a good time to take a break. So that was the first segment of this sixth lecture. Thank you for attending the first segment of this sixth lecture.